Greetings. Now in this part we will prove competitiveness of the list algorithm in the presence of advertisements. So the competitiveness of the list algorithms for the case of the related parallel machines setting. So related parallel machines. Okay, which was just covered by the previous video. So what do we have here? We have a list algorithm, right? And we've seen that in the previous part that by giving a bad input we will have something log m related, something times log m related lower bound, but now we will prove an upper bound, which means that we will have to study all the possible sigma inputs. So let's sigma be, say, p1, p2, p3 and so on, pn be some arbitrary input, be an input, and we will have some v equals, say, v1 blah blah vm, be the speeds, and we will have L star as the optimum, and L is the cost of the schedule produced by the list algorithm. The list algorithm. Okay, so I will prove something that L divided by L star is at most something. So we will prove something like L divided by L star is at most something, and this something will be around log m, where m is the number of machines. Now for this we will have two lemmas. I will prove these first. So after we run the list algorithm, the fastest machine will have a load at least L minus L star. We've seen that in the previous examples that the fastest machine gets a quite large number of jobs. Now it's not always the case that the fastest machine has the largest load, always. But of course, this lemma says that it will have quite a large load all the time. So a lower bound for the load. So to prove this, so first, if the fastest machine has the largest load, then its load is L. So if so let's say the fastest machine's speed, so the fastest machine will have J, say, max, and V max is the fastest possible speed. Right? Fastest speed. I will use this notation in this lemma and in the next one as well. So if the fastest machine has the largest load, then it's L. Then the load of this machine is L, which is of course at least as large as L minus L star, so it's fine because L star is positive, so non-negative, whatever. Otherwise, I will draw some pictures for this. So we will have this machine of speed Vmax, and we have some load. Now some other machine, say Vj, has a load which is larger than the Vmax, and on this machine we have the last job. So it's, let's say it's P, say L, PL. Now, what does it mean? It means that when we, at this time point, when we scheduled here, so this guy is L, okay? So at that time point when we scheduled the job PL, then we had that L. So of course here we had some load for the fastest machine here as well. So it was the load of the fastest machine plus the job PL cost divided by the fastest speed, and this here was at least as large as L, because the load of this machine was of course L minus PL divided by Vmax plus PL divided by Vj, I mean. So here, because we scheduled on this machine, it means that at this point the load of max plus this guy was larger than L. And remember that this PL divided by Vmax, this guy is at most L star, because there was a bound for the optimal cost that PL, so even if we schedule the job PL to the fastest machine, then we will take at least PL divided by Vmax time, and of course we have to schedule the other jobs as well, which means that this is at most L star, which means that we have L star plus load of max at that point of time is larger than L, which means that the load of the fastest machine was already at least L minus L star at that time point, and of course at the end it can be only larger, because if we schedule more jobs to the fastest machine, then its load will be even more. So we already have that the load of the fastest machine is indeed at least L minus L star. Either it's the fastest machine, it's the most loaded machine, or not, no matter. So this guy has a load of at least L minus L star. So that's easy. Now the second lemma is a bit more convoluted, and it says that for any speed v is not necessarily a speed of a machine. It's just a variable which will be interpreted as a speed. For any speed v and say load L, if all the machines of speed at least v have a load at least L, then all the machines of speed at least v half will have a load at least L minus 4 larger star. Right? So this basically says that if fast machines have a large load, then the a bit slower machines will have an almost as large load. Formally, it's just this one. Now, to prove this, again, so if L is at most 4L star, then it's done, because then the statement says that the machines have a load of at least 0, which is always the case. So we only have to prove that if so, it's enough to show for the case of L being at least 4L star. Okay, and again I will draw a picture, an image of a possible schedule according to the list algorithm. So these guys, okay, so these guys will be the fast machines. Fast machine means in this context that the speed of the machine is at least v. And we will have other machines, say mid machines, which we will have mid machines, which are not fast but have a speed at least v half. And there are other machines, they are the slow machines. Yeah. Now, okay. So if we have fast machines, okay, so let's just draw some schedule produced by the list algorithm, okay, as usual. And then we will have these not that fast machines, okay, so the mid machines and the slow machines as well. Okay, now let's just draw something here. It says that the fast machines have a load at least L, so this guy can be taken to be L here, and L being at least 4L star means that I can just draw a window here of width 2L star, and I will be still in the positive part, right? So let's just see this rectangle, and let's consider all the jobs which have some intersection with this rectangle, which means that I will take this job and this job and this job, because these jobs intersect the rectangle of these. So only for the fast machines, I'm just listing all the jobs which either start after 2L star and before L, or they are ending after 2L star and before L. Right. Okay, so all the jobs having a non-intersection with the rectangle I just indicated, so it's just L minus 2L star. Okay. Now I say that there is a job which is scheduled on a node. So in an optimal schedule, one of these jobs is not scheduled on a fast machine. Okay, because if all the jobs are scheduled here, then otherwise the make span would be at least 2 L star, which is larger than L star, which is the optimum. So otherwise the optimum would be at least 2 L star, because if we schedule all these jobs to these machines, then the cost, these guys, the load on these guys will be at least, the maximum load would be at least 2 L star on these machines. So okay, so let this be the job, say. So let this job be this pj, right? Usually j indexes machines, but nevertheless let it be pj. Now, since we have to schedule this job as well, we have that pj divided by vmax is at most L star, because this is the general bound. We have to schedule each job, and we schedule this job by star. Now, this guy here can be improved, because if this job pj is scheduled, not scheduled in a fast machine, then it means that it's scheduled in a slow machine in an optimal setting, and if it's scheduled in a slow machine, then the speed of this machine will be at most v, which means that pj divided by v is at most L star. Now, this means that on a machine of speed at least we have the processing of this job takes at most 2 L star, of course. Processing of pj takes at most 2 L star time. See, if pj divided by L is at most L star, because we schedule the job pj in an optimal setting to the machine having speed at most v, this means that on that machine the load is at most L star. So this means that the pj divided by v half is at most 2 L star, right? I'm just multiplying by 2 both sides. Actually, I'm multiplying the fraction by 2 by halving its denominator, which is fine. So pj takes at most 2 L star time, which means that if one of, so when we run the list algorithm, so running list, if running list ranks list one of the mid machines, which have the speed of at least v half, mid machines would have a load at most L minus 4 L star. Then on this machine, if we just add the cost of pj divided by the speed of machine, that would be at most 2 L star. So the sum would be at most L minus 2 L star. So the sum would be at most L minus 2 L star, which means that we would have been scheduled this job not here, but on some mid machine, because on the mid machines the sum would be at most L minus 2 L star, and on this particular machine it's clear, because it intersects this rectangle, that the cost, the optimal cost the locally optimal cost of scheduling this job according to the list algorithm would be larger than L minus 2 R star, which means that this case cannot happen. So it's because otherwise we would be scheduling this job to a mid machine, which means that each mid machine has a load at least L minus 4 R star, because otherwise we would not schedule this job Pj according to the list algorithm to this particular fast machine which we've done. Right. So we have proved two lemmas. One lemma says that the fastest machine has a load of L minus L star at least. The second says that if we have a speed and a load such that all the machines of this speed have a load at least this guy, then the machines having half the speed have a low, not that much smaller load. Okay, so let's just continue how we use these lemmas to prove this theta logm competitiveness. Again, we will have fast machines. So we have fast machines, those guys which have a speed at least V max divided by M. Slow machines, the others. Okay. Now let's just bound the total load, the load of the fast machines. So if we have a machine which has speed at least V max, then the load, its load is at least L minus L star. Well, this was lemma 1. Now applying, so this was lemma 1. Now applying lemma 2 on this particular inequality, we get that if a machine has at least V max half speed, then the load, its load will be at least L minus L star minus 4 L star. This is lemma 2, which is of course L minus 5 L stars. Now again, we just apply lemma 2. So if we apply lemma 2 at this point, then we get that the machines of speed at least V max divided by 4, because we can halve this speed again, then the load of these guys will be at least L minus 9 L star, because we already have minus 5, minus 4 more, it's minus 9. And then we apply the lemma 2 again, V max divided by 8 speed. Each of these guys we have a load of at least L minus, well, 13 L star, and so on. I do this log m times, right? So it's, if I have the machines of speed at least 2 to the log m, say upper ceiling, then the load of these machines will be at least L minus, okay, so it's 4 log m plus 1 times L star. Why am I doing this? Because this guy here is at least V max divided by M. So these machines are, so it means that all the fast machines have a relatively large load. So the fast machines have this load, at least, or even more. So the fast machines have this load, each of them. So, how much space do I have here? Not that much, okay. Okay, so fast machines have a load of at least as large as this. Now, so the total work, which means that the total work, so the sum, so let W denote the sum of the total size of the jobs, right? So if all the fast machines have a load, at least this one, then this means that the total work is, well, at least the sum of the speeds of the fast machines times this L minus 4 log m plus 1 times L star times L star. Okay. And also we had found previously that the total work is at most the sum of all the speeds times R star. That was our very first bound, very first lower bound for the optimal cost R star, written in some other form. So the total size of the jobs is at most so it fits into the rectangle defined by an optimal schedules work rectangle sort of thing. Now this is just the same as if I'm just splitting this sum into two partitions. First I'm just writing out the sum of those j's which are fast, vj, times L star plus the sum of those speeds vj which are slow times L star, right? So I'm just partitioning this sum of all the speeds to two parts, so I'm just summing the fast machines separately and summing the slow machines separately. Now, okay, because this is something we have seen already, so okay, because the sum of the fast machines appeared here as well, so we just have to rewrite this part, but this part is relatively easy to rewrite because this guy here is at most, say, since the machine is slow because its speed is at most v max divided by m, so it's at most, so j slow, each of them being at most v max divided by m. And how many slow machines we can have? Well, at most m, because we have at most m machines, so we have at most m slow machines. So this means that this is at most v max, because we have at most m machines, each having a speed of at most v max divided by m, which means that the sum of these speeds is at most v max. Now, the v max is a speed of a fast machine, which means that the Vmax is at most the sum of those j's speeds which are fast. If you only have one fast machine, then the sum of the speeds will be Vmax exactly. But if you have at least two fast machines, then this sum is larger, still larger than Vmax, but we only need this. So it's at least, at most, the sum of the speeds of the fast machines. So basically it says that the total speeds of the slow machines is at most as large as the total speed of the fast machines. Well, it's not that, it shouldn't be that surprising, I would say. Sorry for the advertisement bouncing in, but now I will have this. So from this reasoning, I can get that this thing is at most as large as 2 times the sum of the speeds of the fast machines. Of the fast machines, I'm just tracing this guy back, and I will see how much space I have left. Oh, it's more than enough. So I will have this total speed of the fast machines. So I have 2 bounds right now. For this W, I have this W is at most as large as 2 times the speeds of the fast machines total times L star, and it's larger than this product of the speeds of the fast machines times this amount. Which means that if I just write this down and I just divide, and I just cancel this term. That's why I made this thing. So I made this in order to be able to cancel this term here and there, and I can write that L minus 4 times log m plus 1 times L star is at most as large as 2 times L star, which is great because this is the same as saying that L is at most 4 times log m plus 3 times L star, which is the same as stating that L divided by L star is at most 4 times log m plus 3. This is just a theorem about the competitiveness of the list algorithm for the case of related parallel machines, that the competitive ratio of this algorithm is something like log m. So the list algorithm is, we denote this by O, big O notation. If you haven't learned it in your bachelor studies, then please look it up on wiki. So it basically says that the leading term of the complexity of this function is some constant times log m. Is log m competitive? So we have just proved that for any input sequence, the list algorithm will produce something times log m competitive output, which means that it will not exactly match our lower bounds. So we had a lower bound of, say, it was just log m divided by 2 or something like that, and this is the log m multiplied by 4, but it means that the actual competitive ratio of the list algorithm in this setting is somewhere around log m, so it's theta log m to be more precise. So basically that's all what we should know about scheduling algorithm for the version where we have parallel machines. Next time we will introduce timings as well, timestamps, arrival times, which is again a really real life scenario, but for now it's enough because this proof is one of the hardest proofs available during the whole semester, so I'll just stop here, and next time I will talk about the time model of the scheduling problem. Till then, bye bye.